Cancer is a term that we've all heard before. It's more than just a diagnosis. It's a term that causes tightening in the chest, a term that brings with it dread and the fear of the unknown. When we think of cancer, we think of the battle, the loss, and the what-ifs. Among the many forms of cancer, leukemia stands out in particular. It is a cancer of the blood and the bone marrow that affects over 66,000 adults each year, and is the most common form of cancer found in children. But what if I told you that there was hope? What if, instead of fearing cancer, we could fight with our own body? Imagine if there were a technology that empowers our immune system, giving it new instructions to recognize and destroy specific cancer cells. What if we could equip our white blood cells with a GPS, programmed to locate and destroy cancer cells at their roots? Today, this is no longer science fiction. It is the reality with CAR-T therapy. This year, I had the chance to explore this novel technology in treating acute myeloid leukemia. From my initial research, I found that Hong Kong, the city I was born in, has become a powerful hub for this type of innovation. What's fascinating about it is that Hong Kong is consistently ranked among the highest in average life expectancies globally. In fact, it surpassed the leader of longevity, Japan, in 2013. From 1979 to 2016, the expected lifespan in Hong Kong increased by a difference of 1.86 years for males and 2.5 years for females. And by 2024, there is an average life expectancy of around 85.25 years. To put this in context, the rest of the Greater Bay Area, like Guangdong Province, right next door, has an expectancy of just 77.3 years by the end of 2020, which is a whole 8 years less than Hong Kong. And Macau, another special administrative region with similar cultural backgrounds to Hong Kong, has a life expectancy of only around 83.4 years. So, what is the secret behind Hong Kong's leading life expectancies? Of course, the answer to the leading longevity isn't a simple one factor. But one thing does stand out, which is the tight integration of medical research and clinical practices. In Hong Kong, medical breakthroughs don't just remain in published scientific papers and behind paywalls. They are brought to life in hospitals. Patients become the direct beneficiaries of these cutting-edge innovations. In the context of leukemia, greater medical research has led to more development in existing therapies and access to new innovative treatments. And it is these tangible treatments that drive a greater chance of survival and remission. Ever since 1973, the conventional best treatment for leukemia has long been chemotherapy. Its primary objective is to remove as much leukemia and myeloblasts as possible using cytotoxic drugs. In other words, chemotherapy aims to eliminate excessive immature white blood cells, preventing them from occupying the space and nutrients inside the blood. However, because this drug used in chemotherapy targets all blood cells indiscriminately, normal healthy blood cells within the bone marrow are destroyed along the cancer cells. It's like using a flamethrower to kill weeds. The flamethrower is the chemotherapy, and the weeds are the intractable cancer cells. Sure, it burns the cancer, but it also destroys the healthy blood cells along the way. This weakens the patient's immune system, which can often lead to severe side effects and death. Since then, other treatments like stem cell transplant, targeted therapy, and radiotherapy have also been discovered and used to help reduce the disease relapse rate from leukemia. Each of them is better in some ways, but still imperfect. Many patients relapse, cannot achieve complete remission, and experience treatment rejection on multiple occasions. With most conventional technologies, leukemia is more like a weed that is not fully trimmed out every time. You pull out the leaves and stems above the ground, but the underground roots are still alive. Slowly, these parts will grow back stronger and start to spread faster. These limitations hinder the development progress in these treatments. This is where CAR-T therapy changes the game. Due to the therapeutic limitations of conventional treatments for leukemia, the immunotherapy-based chimeric antigen receptor T-cell therapy, also known as CAR-T for short, has emerged as a key area of focus. Think of it this way. CAR-T essentially reprograms the T lymphocytes in our immune system to express a chimeric antigen receptor, which is the CAR in the CAR-T. This CAR is like a detector that hunts for the name tag or the antigen on the specific leukemia cells. It acts like a living drug. Instead of providing additional chemicals or substances to attack the cancerous cells, CAR-T reprograms the patient's own lymphocytes in their immune system so that their T cells can tackle the specific malignant cells only while having minimal side effects on the normal blood cells. In 2020, Hong Kong became the first in the Greater Bay Area to perform the CAR-T for a lymphoma patient at the University of Hong Kong. And soon after, following this breakthrough, Queen Mary Hospital became the first Hong Kong institution to provide CAR-T as a clinical therapy for a range of blood cancers, including patients with leukemia, lymphoma, and myeloma. So far, this technology has been used on over 60 blood cancer patients, making Hong Kong the regional leader in the clinical use of CAR-T. While much of the mainland Greater Bay Area is still in the research or trial phase of CAR-T, the advancement of CAR-T research in Hong Kong is much more established and has moved into real-world application. This is a game changer for leukemia patients because it means a greater chance of survival and remission, especially for those with a high relapse rate. To better explain how CAR-T works, we first have to understand the function of our immune system under normal circumstances. Usually, our immune system consists of many white blood cells. They are like guards working together to defend against the harm from foreign invader cells. One specific type of white blood cell is the lymphocyte. These lymphocytes can be classified under two main branches, which are the B lymphocytes and the T lymphocytes. Both types of lymphocytes are produced in the bone marrow. But while the B lymphocytes continue to mature in the bone marrow, the T lymphocytes will go on to mature in the thymus. These lymphocytes will then have different properties. For example, the main purpose of the B lymphocytes is to produce chemical tags called antibodies. This tag binds to the invader cells to warn the immune system of this intrusion. In contrast, the T cells differentiate to form 4 different cell types: the T killer, helper, memory, and regulator cells, which collaborate together to kill foreign cells. Now, to relate these cells to CAR-T, we will focus on the T cells specifically. In a leukemia patient, when a surveillant phagocyte encounters an invading foreign cell, it will express the specific foreign markers on its surface so that T lymphocytes can undergo clonal selection to pick the T cells with a complementary receptor to the marker. After selection, the T cells replicate themselves to form multiple identical cells, which will then differentiate into T helper and killer cells. The T helper will release messengers to signal the T killer cells. And when released, these tiny chemical messengers will direct the T killer cells to the target foreign cell, ensuring that the T killer cells can respond and destroy these leukemia cells as efficiently as possible. However, due to the time-consuming nature of the selection process, the T cells capable of fighting cancer are generally in low numbers. Therefore, CAR-T comes in here to fast-track it. Creating CAR-T cells is like upgrading the T cells from the patient with a special targeting system. The scientist will take the part of the antibody that can attach to a specific target on the cancerous cell and combine it with a T cell's attack signal. This forms a new receptor, which is the CAR, that allows the T cells to find and attack specific cells. This upgraded version of the receptors will then be reintroduced into the T cells using truck-like delivery tools. Once the T cells are modified, they are then expanded in numbers and infused back into the patient's blood. These CAR-T cells now have a GPS ability to locate and destroy harmful cells more effectively, just like T cells do naturally, but with a more targeted focus on the specific cancer cells. Currently, CAR-T therapy has been approved in multiple countries with extensive use across Europe and China. Interestingly, the majority of research on CAR-T therapy actually originates from China, but Hong Kong stands out with a greater integration of research with real patient healthcare. This creates a powerful feedback loop where medical innovations translate into better practice, with results seen in patients, which in turn can fuel more research and innovation. By looking at Hong Kong's life expectancy statistics, we see a direct link between its preventive strategies for non-communicable diseases and its positive connection to higher survival rates. This success can in part be due to the city's robust research and healthcare system, which effectively addresses both poverty and affluence-related diseases. This is not only reflected in leukemia patients, but also in other severe health conditions. In recent years, the increase in life expectancy has been caused by the decline in cancer and cardiovascular mortality rates. For example, research shows that a lower cancer mortality leads to an increase of an average of 0.47 years in females, and a decreased cardiovascular death rates lead to around 1.22 years and 1.19 years longer for males and females, respectively. Therefore, this healthcare system can be referred to as a model for the Greater Bay Area and beyond. It shows that when innovation meets the proper practices, health outcomes can significantly improve even in the face of complex diseases like leukemia. Looking ahead, the potential of CAR-T extends far beyond its current applications. CAR-T has already shown incredible results for B-cell acute lymphoblastic leukemia and multiple myeloma. But now, scientists are pushing this boundary to greater lengths. Ongoing clinical trials and research are expanding its use to more blood cancers with higher relapse rates, like acute myeloid leukemia, which historically have fewer treatment options and lower survival chances. So, what does this all mean? It means that we are no longer fighting cancer with hope. We are fighting it with precision, science, and our very bodies. And with cities like Hong Kong, it shows what's capable in the next wave of CAR-T development when biomedical research and clinical translation go hand in hand. Ultimately, the city's healthcare model underscores a powerful truth. When research innovation is tightly woven into clinical practice, CAR-T doesn't just extend life, it redefines what is possible in the fight against cancer.